Now we will discuss third application of Gauss theorem. So electric field intensity at a point near and outside a charged conductor of any shape. So third application is E at near point and outside a charged conductor of any shape. Now for that we will consider a conductor of any shape and on which charges are deposited. So this is a charged conductor of any shape placed in a medium of permittivity epsilon. Epsilon is equal to epsilon 0k. Now consider small area ds of this charged conductor and take a point P just outside this charged conductor and point Q which is inside this charged conductor, and then construct a cylinder with x6 is equal to PQ, and therefore this cylinder PQ encloses the area ds. Again, if sigma is the surface charge density, then charges deposited on area ds becomes Q is equal to sigma into ds. And at point P, again here electric intensity is directed radially outwards, but the electric intensity inside this charge conductor is 0 because it does not encloses any charge. Again, by using total normal electric induction over a Gaussian cylinder, we write T and ER is equal to epsilon E into ds. Suppose this is equation number 1. Again, by using the Gauss theorem, total normal electric induction over ds is equal to charge enclosed by the area ds, and which is equal to sigma into ds. Say this is equation number 2. Then by comparing equation number 1 with equation number 2, we get epsilon E into ds is equal to sigma into ds. ds gets cancels, and therefore electric field intensity at a point outside and near to the charged conductor of any shape is equal to sigma divided by epsilon, or which is equal to sigma divided by epsilon 0k. So this expression is useful while discussing the mechanical force on unit area of a charged conductor. So this is all about third application. Now last application of Gauss law or Gauss theorem is electric field intensity due to thin large plane sheet. So fourth application is electric intensity due to a thin large plane sheet. And for this we consider a thin large plane sheet. So this is a thin large plane sheet on which charges are deposited. As this is a plane sheet, it has two surfaces. Now, to find electric intensity, we have to construct an imaginary cylinder. So construct imaginary cylinder which is passing through the center of this plane sheet, and the two surfaces of this cylinder are outside the plane sheet. So this is the Gaussian cylinder, and this Gaussian cylinder having two surfaces, small area ds, and this cylinder encloses the charge which are deposited on the plane sheet. Again, by using total normal electric induction. So total normal electric induction over cylinder or Gaussian cylinder, which is equal to epsilon E into ds. But here in this case, as we have to find the value of electric intensity due to thin large plane sheet, and there, as the sheet possesses two surfaces, we write T_N_EI is equal to epsilon E multiplied by 2 times ds. So this is expression number 1. And again, if sigma is the surface charge density, then charge on area ds is given by q divided by ds, as q is equal to sigma into ds. So T_N_EI again over cylinder is equal to sigma into ds. So this is equation number 2. And by equating these two equations, we get epsilon E into 2 times ds is equal to sigma into ds. So this ds gets cancels, and we get electric field intensity due to this large thin plane sheet. E is equal to sigma divided by 2 into epsilon, or which is equal to sigma divided by 2 epsilon 0 k. So this is the expression for electric field intensity due to thin large plane sheet. And we observe that in this expression the term distance of the point from the plane sheet is absent. Therefore this electric field intensity is independent of the distance from the charged plane sheet. So in today's lecture, we have discussed all the applications of Gauss theorem. Now in next lecture, we will solve some numericals which are based on the applications of Gauss theorem. So in this numerical, we have given infinite line charge and which produces electric field of 9 into 10 to the power 4 Newton per Coulomb. So E is equal to 9 into 10 to the power 4 Newton per Coulomb at a distance of 2 centimeter. That means distance is given, which is R, which is equal to 2 centimeter, equal to 2 into 10 to the power minus 2 meter. And we have to calculate the linear charge density, which is lambda. We know the formula. The electric field intensity at a point outside a charged cylinder is given by formula 1 upon 2 pi epsilon into lambda divided by small r. Or this can be written as 1 upon 4 pi epsilon 0 into 2 lambda divided by r. if we substitute the values, or E is equal to the value of 1 upon 4 pi epsilon 0 is, we know that it is 9 into 10 to the power 9 multiplied by 2 into multiplied by lambda divided by radius is given, which is 2 into 10 to the power minus 2. So 2 into 10 to the power minus 2. Again these two gets cancels. Therefore term remaining on the right hand side is 9 into 10 to the power 11 into lambda, and hence lambda is equal to E divided by, so the value of E is 9 into 10 to the power 4, so 9 into 10 to the power 4 divided by 9 into 10 to the power 11, and which is equal to 10 to the power minus 7, and SI unit of electric field intensity is Newton per, SI unit of lambda, that means linear charge density, is Coulomb per meter.
Okay.
Second numerical, calculate the surface charge density of charge on a metal sphere of radius 10 centimeter. That means charges are deposited on a sphere having radius 10 centimeter, that means capital R is provided, which is 10 centimeter equal to 10 into 10 to the power minus 2 meter is equal to 10 to the power minus 1 meter. Again, it is situated in air, therefore dielectric constant of the medium is 1, and we have to find the electric intensity at a point at a distance 20 centimeter. So electric intensity is given, which is at a distance of 20 centimeter, which is 10 to the power 5 Newton per Coulomb, and the electric intensity at a point, that means small r is provided, which is 20 into 10 to the power minus 2 meter, which is equal to again 2 into 10 to the power minus 1 meter. So in this case, we want to find the surface charge density, and we know the expression for electric field intensity in terms of surface charge density. So E is equal to sigma into capital R square divided by epsilon into small r square, or which is equal to sigma into capital R square divided by epsilon 0 k into R square, and hence sigma, that is surface charge density, is equal to epsilon 0 capital E into small r square and divided by capital R square. Now substitute the values of epsilon 0, which is 8.85 into 10 to the power minus 12, electric intensity, which is given 10 to the power 5 Newton per Coulomb, into small r square. Small r is given 2 into 10 to the power minus 1, and its square is 4 into 10 to the power minus 2 divided by capital R square. Capital R square is 10 to the power minus 1 and its square is 10 to the power minus 2. And therefore we get 8.85 into 4 into 10 to the power, this is minus 12, plus power 5 minus this power minus 2, and this power goes into the numerator, becomes plus, which is plus 2. And if we multiply 8.85 by 4, then we will get 35.40 into, if the powers are connected, then minus 12, minus 2, minus 14, and plus 5 plus 2 is 7. So minus 14 plus 7, which is equal to 10 to the power minus 7, and unit for surface charge density is Coulomb per meter square. Third problem on applications of Gauss theorem. A conducting cylinder having charge density, that means sigma, which is equal to 100 nanocoulomb per meter square, which is equal to 100 into 10 to the power minus 9 coulomb per meter square, or which is equal to 10 to the power minus 7 coulomb per meter square. And the radius of the cylinder on which charges are deposited is given, that means capital R is equal to 36.40 millimeter, which is equal to 36.40 into 10 to the power minus 3 meter. And dielectric constant of the medium is given, which is K equal to 4. And we have to find the electric field intensity at a distance small r, which is equal to 1 meter. As this numerical is based on electric intensity at a point outside a charged cylinder, then electric intensity outside a charged cylinder in terms of surface charge density is given by formula E is equal to sigma into capital R divided by epsilon into small r, that means epsilon 0 K into small r. Now substituting the values, E is equal to value of sigma is 10 to the power minus 7 multiplied by the value of capital R, which is 36.40 into 10 to the power minus 3 divided by value of epsilon 0 8.85 into 10 to the power minus 12. Value of K is 4 multiplied by the value of radius of outer cylinder, which is 1 meter, and this is equal to 36.40 into 10 to the power minus 10 and divided by 8.85 into 4, which again becomes 36.40 into 10 to the power minus 12, and therefore we get E is equal to 10 to the power 2. Unit is Newton per Coulomb. A uniformly charged sphere produces an electric intensity 100 volt per meter. So electric intensity is given, E is equal to 100 volt per meter, which is 10 to the power 2 volt per meter. On its surface, in a medium of dielectric constant 5, that means K is given, which is 5. And we have to calculate surface charge density, that means sigma is equal to what? Here we want to find, we are provided electric field intensity on its surface, and therefore here we use the formula, or we apply third application. E is equal to electric field intensity at a point near and outside a charged conductor of any shape is given by sigma divided by epsilon 0 K. And therefore sigma is equal to epsilon 0 K into E, which is equal to 8.85 into 10 to the power minus 12 into value of K is 5 into value of E is 10 to the power 2, which is equal to, multiply 8.85 by 5, we will get 44.25 into 10 to the power minus 10, and again unit of surface charge density is coulomb per meter square. वा लवकरच आहे ना.
पटपट ते
काय मला लय दम लागला. In this numerical, two infinite large metal plates parallel to each other and they are close to each other and the plates have surface charge density of opposite sign. That means on one plate the surface charge density is plus sigma and another plate the surface charge density is minus sigma. And we want to find the electric field intensity between two plates. And we have provided magnitude of surface charge density sigma is equal to 17.7 into 10 to the power minus 20 coulomb per meter square. And therefore the net electric field between the two plates is equal to 2 into electric field intensity due to thin long metal plate and which is equal to sigma divided by 2 epsilon 0 k. So this 2 gets cancelled, therefore net electric field between the two plates is epsilon divided by epsilon 0 k. It is given by sigma divided by epsilon 0 k. And hence we write 17.7 into 10 to the power minus 20 divided by 8.85 into 10 to the power minus 12 which is equal to 2 into 10 to the power 8 Newton per coulomb.